So our next speaker is Seidon Alsaody from Uppsala University, and he's going to talk about exceptional symmetry.
Right. Thank you very much, Arturo, and thank you for the invitation to give this talk. Needless to say, I'm extremely honored to give a talk in honor of Robert Moody. I first met Professor Moody back in Edmonton 5 years ago, and he was incredibly encouraging after my talk at the conference in honor of Arturo Pianzola and Vladimir Chernosov. So I'm very happy to be here indeed. And since this conference is about symmetries, I thought to share some, to give some overview of some recent work that I have done on exceptional symmetries. And some of you have heard some of these results before, so I apologize, but I will try to give an overview that hopefully will be interesting. So what we are dealing with algebraic groups. So as you know, algebraic groups over, say, the complex numbers or algebraically closed fields of characteristic 0 come in 4 classical families. So the classical families are the families indexed by an, for n starting at 1, bn, n starting at 2, cn, n starting at 3, and dn, n starting at 5. And then there are 6 exceptional groups, namely G2, D4, F4, E6, E7, and E8. This might be a bit non-standard, but I hope to be able to convince you that this is the way to view these things. So these are all, I mean, you know, the classification of Cartan killing in terms of root systems and everything. But then one can ask, what is the meaning of these groups? So how do they arise somehow naturally? And I will especially be interested in these 6 exceptional groups. So the classical groups have some very natural realizations that you all know in terms of, you know, symplectic forms and all of that. But for the 6 exceptional ones, it might be a bit of a struggle to find such examples. But then, for instance, G2 can be realized as the automorphism groups of some Octonian algebra. So C is an Octonian algebra. And this will be and is a general theme in this context, that these exceptional groups will arise as automorphism groups of some exceptional other structures like Octonian algebras and other non-associative algebras. And our goal is to understand these exceptional groups over R. And what is R? R is a unital commutative ring. So over fields, these are rather well understood to some extent. And now we're wondering how they look over rings. And the tools we will be using to understand these groups are these other exceptional structures, such as Octonian algebras. So why do we want to consider these things over rings rather than over fields? Well, a prominent object in the contexts related to this conference is that of E8 lattices. And so here you can view this as looking at exceptional groups in the case where your ring is the integers, or some ring related to the integers, some discrete ring in that sense. You can also take R to be the ring as follows. This also famously is connected to the theme of this workshop. In a more geometric sense, you can take R to be, say, C or maybe say the real numbers, bracket M, where M is some manifold or variety. Say smooth manifold or algebraic variety. And you look at the coordinate ring of this variety. And the effect of this is that you're looking at sort of a bundle of structures over this variety. So one prominent example in this direction is that of G2 manifolds. That in what they really are is that they are Octonian bundles over 7-dimensional manifold M. And these are used to give a mathematical understanding of the hidden dimensions in string theory and theoretical physics. So there are various reasons to want to study these objects. And what to expect from this study, from going out over rings, is, well, there will be a lot of non-trivialities. And another way of viewing that is that there will be some lack of miracles. So let me explain what this means. So over fields, some miracles happen that don't happen over rings. And so over rings, these structures come to their sort of full bloom. So let me give you the motivating example of that of Octonian algebras. So what is an Octonian algebra? An Octonian algebra is, well, let's digress to give a definition. So let's start over fields. A composition algebra is a not necessarily associative or commutative, but unital algebra, C, equipped with a non-degenerate, multiplicative, quadratic form. Q. So what multiplicative means is that Q applied to the product is the product applied to each element, like that. What non-degenerate means, I would not want to delve into. It means what you expect it to mean, except if you work over fields of characteristic 2, then nothing is as you expect, but somehow this is expected. So non-degenerate just means nice enough in this context. And the fact is that these algebras exist in dimension 1, 2, 4, and 8 only. And those of dimension 8 are called Octonian algebras. Just as a side remark, this implies that they don't exist in infinite dimension. They are necessarily finite dimension. Now, you can make this definition mutatis mutandis over rings. You replace, so what is an algebra? Well, you require the algebra to be a module that is projective of constant rank 8, and everything else stays the same. And so you have an Octonian algebra C, and you have a multiplicative quadratic form Q. So the groups that are involved here you have the automorphism group of C that sits inside the orthogonal group of this quadratic form Q of C. This is of type G2 and dimension 14. This is of type D4 and dimension 28. And so the inclusion implies essentially that two isomorphic Octonian algebras have isometric quadratic forms. The quadratic form can be obtained, it's presented as an additional datum, but really it is determined by the multiplication of the algebra. This is nothing unusual, nothing unexpected. The question is, does the quadratic form determine the entire algebra structure? And over fields, this is a miracle. The quadratic form determines the Octonian algebra up to isomorphism. The remarkable thing, so it was believed that this held in general until Philippe Gilles proved that this was not the case. So this gave some motivation to trying to understand these objects over rings. So what does this mean for us? Well, there are several ways to interpret this. So the algebraic meaning of this is that Octonian algebras over rings are not determined by their norm form. This is essentially the title of Philippe Gilles' paper. So the Q, what I just wrote, does not determine C. But now we have digressed to the level of Octonian algebras. What does it mean geometrically? Well, it means that the G2 tensor, torsor, I mean, I'll explain what this is and motivate my sloppy notation. This is non-trivial. Or another way to put it is that groups of type D4 contain subgroups of type G2 that are not conjugate. So what this here means is that, well, you have G2. So G2 here we view as the automorphism group of our Octonian algebra. And to have connectedness, D4 is SO of the quadratic form Q. And so I told you that this sits inside this one, so we can take the homogeneous space. Fibers will be twists of the group G2. And then you have this projection. This gives you a torsor fibration, if you wish, or a principal homogeneous space. And this fibration is non-trivial. It doesn't decompose as a product space. So this torsor is non-trivial. And then you want to see, okay, so what does this mean and how can we understand it? Because this homogeneous space is somehow, well, abstractly it's clear what it is, but what does this actually look like? So this needs to be something of dimension 14. And what does this projection look like? So this is what I will now tell you as a motivation for what comes ahead. Maybe I should stop and ask for questions or remarks at this point, or should I just continue? I take your silence as encouragement, so I will continue. So in order to understand this, we tried to understand the various parts of this torsor together with Philippe Gilles. And so the highlights is that this homogeneous space, D4 mod G2, this is isomorphic to 2 copies of the 7-dimensional sphere. The 7-dimensional sphere here is the set of all elements in the Octonian algebra such that Q of X is equal to 1. And the torsor parameterizes all the so-called isotopes of Octonian algebras. So I will get into details later. So the first part is the geometric part, telling us what this thing is, and the second is the algebraic part, relating this to an algebraic construction. So this can be seen as a sort of a starting point for a way of thought where, okay, so we have now groups of type D4 can be realized as G2 torsors over some geometric space, which we understand rather concretely. So what about the other exceptional groups? So let me draw you this picture. So we have D4 as a G2 torsor over this S7 times S7. So now somehow we claim to understand D4. What about the next thing? Well, one can realize groups of type F4 as D4 torsors over some space F that I will define later. So this notation means that the group here on top, in this situation F4, has a projection down to some geometric space that we understand. And this projection is not just a random fibration, it's a torsor. It's a principal homogeneous space, which means that the fiber over every point is a twist of this group, D4. So this gives us F4, and then one can realize groups of type E6 as F4 torsors over some other geometric space, and then groups of type E7 can be realized as E6 torsors over some other space. And now I run out of height, so I will stop here, which is convenient because it still needs to be done, how groups of type E8 relate to this. So I will now describe how this, so this was what I already briefly mentioned. I will develop this more. Then I will go into this fibration and make it more precise and explain what it classifies. And then go into this. And time permitting, I will mention this part, which is a work in progress still. Also in relation to 2, there is 2 prime somehow, where you can take F4 on F4 mod G2, and this will be a G2 torsor. Okay, so let me go into this in more precise terms. So let's start with part 1. So now I take C, an Octonian algebra, over my ring R. R is always a unital commutative ring. And so remember, this has a multiplicative quadratic form Q, and it also has an involution. So if you're working over the real numbers, then the octonians are just an 8-dimensional version of the complex numbers, and this involution corresponds to complex conjugation. And so coming back to the joint work with Philippe Gilles, we want to understand the group of type D4 and their SO, the special orthogonal group has a simply connected cover, which is the spin group. And the spin group can be realized in a peculiar way. It can be realized as all the triples belonging to SOQ cubed, with the property that applying the first one to a product of octonions equals applying the second to X, the third to Y. The fact that spin Q has this property, this is the principle of triality. It was first established over fields by Élie Cartan in 1925. For technical reasons, we will alter this a bit and use this version. So we apply the involution here and there to get some nice technical properties. But other than that, this is a sort of generalization of automorphisms of the Octonian algebra. T1 of xy equals T2 of x, T3 of y. And so these are viewed as the name for this is that they are the triality components of T1. And they're somehow essentially determined by T1. And so now to get this projection of D4 onto the 7th sphere, so let me by 7th sphere again, I mean the set of all x in C such that Q of x equals 1, the unit sphere. By the way, I am using rational points notation here. So really all of these are functors. This is a group scheme and this is a scheme. And so really you should say that for all ring S over R, but this gives you the general idea and nothing strange happens as you go up. So I think this is the more transparent way of viewing these objects. If you are into group schemes, just think of the scheme version of this. So now how does spin of Q act on the product of S7 with S7? Well, a triple acts on a pair AB simply by T3 of A, T2 of B. So morally, you view this as T1 acting on a pair AB via its triality components. And the stabilizer, so a prominent element of the Octonian algebra that has norm 1 is the unity. And so the pair 1, 1, so 1, this is the unity of the Octonian algebra. This is the automorphism group of C. So you have an action of spin Q on S7 times S7. You have a point whose stabilizer is OC C. And so working out the details, you get that you have spin Q over S7 times S7 is an OC torsor. And here comes the geometric part. It's an OC torsor with respect to the FPPF topology. What does this mean? This means that this projection is not honestly surjective. But it becomes surjective if you extend scalars, or rather if you take a base change. So if you're working over R, this will not be, there will be points here that are not hit by this projection, but after a nice enough base change, this will become surjective. And nice enough, in our sense, is FPPF, faithfully flat of finite presentation. So some scalar extension that affords this surjectivity. And then the so the fiber of AB in S7 times S7 is a twist of the automorphism group of C. So let's call this twist EAB. And if you follow the yoga of torsors, it can be used to twist your Octonian algebra. And the main result of that paper, so when you twist C, you get some algebra that is usually denoted AAB twist C. This is a formal procedure because the group that governs the fibers is the automorphism group of C. There is a formal procedure to twist the algebra C by the fibers. But this is abstract, and so we wonder, what does this twist look like? And in fact, what we managed to prove is that this twist is canonically isomorphic to an algebra denoted CAB, which is just C with a new multiplication instead of taking the usual multiplication in C, you multiply in these elements A and B. So a very concrete algebraic construction. So this now, hopefully, even if the technicalities are not in themselves interesting, give you the idea that hopefully in favorable situations, these torsors can be understood in a rather concrete way. And this will help us understand the exceptional groups, because now all groups of type G2 that fit inside this group of type D4 will be automorphism groups of these very concrete algebras. So we can give formulas for them explicitly. And so coming back to this picture, we would like to do the same for step 2, 3, and 4. This will give us some additional understanding of the groups that are involved. And so for parts 2 and 3, and even in fact part 4, we need to find some algebraic structure that plays the role of Octonian algebras to model our objects, to model our groups. And so this brings us to the definition of Albert algebras, or if you wish, exceptional Jordan algebras. So for the purpose of this talk, I will assume that 2 is invertible in my ring. This is not necessary. The results hold even when 2 is not invertible, but the definitions are more complicated. So let's stick with the 2 invertible case. So what is a Jordan algebra to begin with? A Jordan algebra over R is an R module J together with a distinguished element, or let's write this in a more understandable way, that it is a unital commutative R algebra, commutative but not associative. It satisfies a weak form of associativity known as the Jordan identity, which looks like this. So this might look unmotivated as a definition, but the main example, so if you think about it, the definition of Lie algebra with the Jacobi identity may look strange when a student sees it the first time, but then the example is that, okay, you take an associative algebra, you take the commutator, it will be a Lie algebra. Here the same. So if you take A, an associative algebra, and you define a new multiplication, which is the anti-commutator, then this is a Jordan algebra. That is denoted A plus. And so if a Jordan algebra is a subalgebra of such an algebra, then it's called special. So a Jordan algebra is special if J injects into some A plus for some associative algebra. Otherwise, it's called exceptional. And over an algebraically closed field, there is, say, over the complex numbers, there is exactly one exceptional Jordan algebra up to isomorphism, and that is the one called the Albert algebra. So an Albert algebra is just an exceptional Jordan algebra. And so what is, how do we construct this? So well, let's say over an algebraically closed field. How do you construct the exceptional Jordan algebra? Well, you take C, an Octonian algebra, and you denote by H3 of C the set of all Hermitian 3 times 3 matrices over C. So C has a conjugation, has an involution, and so it makes sense to consider this this object. So concretely on the diagonal, you will have scalars, and here you have C1, C2, C3, let's say, and then C1 bar, C2 bar, C3 bar. So scalars on the diagonal and these things. And if you do a dimension count, you have 3 here, plus 8, plus 8, plus 8. So this has dimension 27. And you can always define, so this is over algebraically closed field. Over algebraically closed field, every Jordan algebra, every exceptional Jordan algebra, every Albert algebra is of this shape. In general, this thing can be defined over any ring. So this can be defined over rings. And any Albert algebra over R is FPPF locally isomorphic to H3 of C. They all, in fact, become isomorphic. So this means that after a reasonable scalar extension, your algebra will look like this. So this description relates groups of type, well, they relate Octonian algebras to Albert algebras and groups of type G2 to whatever the automorphism group is of these algebras. And so it is well known that the automorphism group of an Albert algebra is of type F4. Okay. So now this brings us one step closer to wanting to understand groups of type F4 together with groups of type D4 in terms of these objects. And one notion that turns central in this is the notion of a frame. So a frame of an Albert algebra is a triple of orthogonal idempotents of rank 1. Rank 1 is a technical condition here, but it's somehow triples of distinguished idempotents. And the main example to keep in mind is the triple E1, E2, E3, where EI is the diagonal matrix with 1 in position EI. So for example, E1 is 1, 0, 0, 0, 0, 0, 0, 0. And E2 in the middle and E3 below, and so on. So then we set F as the set of all frames. So let me be more precise. So F sub j, let this be the set of all frames of the Albert algebra J. This turns out to be a variety of dimension 24. And now we can state some results. So the automorphism group. So I should say that over fields, these results are well known. Now over rings, they are seemingly new. So the automorphism group of the Albert algebra, let me, denote that H3C or J. This acts on the set of frames. And this action is locally transitive with respect to the FPPF topology. So same history as before. And the stabilizer of this particular frame, E1, E2, E3, this is actually spin of QC. The spin group of the quadratic form of the Octonian algebra that we started with. So I remind you that the spin group had this realization as these funny triples, and basically such a triple acts on C1, C2, C3 in a way that's compatible with the multiplication. I should also have said that when we look at the Albert algebra, the multiplication of the Albert algebra is the anti-commutator again, so that the anti-commutator of two Hermitian matrices is still Hermitian. And so this implies, so this is one thing. This implies that the automorphism group of H3C mod the spin group of QC is isomorphic to F. So this gives us a torsor aught H3C onto F that is a spin QC torsor. So this is this situation of F4 over F being a D4 torsor made precise. So this is an FPPF torsor. And so now two questions arise. First of all, what is this torsor non-trivial? And the second question is, what does it classify? So the first proposition is that this torsor is non-trivial. So there are, which perhaps is not news, the groups of type D4 sitting in this particular way inside F4 that are not conjugate. But now the question is, what does this classify? So what does this mean? Well, in the Octonian algebra case, the point of the torsor that was used there was that it classified Octonian algebras that had the same quadratic form. Octonian algebras that were not isomorphic but had the same quadratic form. In this case, it turns out that this classifies compositions of quadratic spaces that give rise to isomorphic Albert algebras. So what does composition of quadratic spaces mean? It's a generalization of a composition algebra. So it's a triple of quadratic spaces of the same dimension. So a triple CI QI, I goes from 1 to 3, with a multiplication let's say that the multiplication goes from C3 times C2 to C1 that is compatible with the quadratic forms. So it's a generalization of an Octonian algebra. And these are non-degenerate rank 8. And so this is what this classifies. And then this, and so from such objects, you can build these Hermitian matrices in a similar way that you can from ordinary Octonian algebras. You get an Albert algebra, and this is what it classifies. This might be non-satisfactory because we were hoping to say something about Octonian algebras. So what the non-triviality of the torsor now is saying is that it does happen that different compositions of quadratic spaces give rise to the same Albert algebra. But now the question is, can this still happen? Can this non-triviality still happen if we require that these are not these generalized compositions of quadratic spaces, but honest to goodness composition algebras, honest Octonian algebras? And the answer is yes, we can. So as a remark, this can be refined. I will not go into the details, to imply that there exists Octonian algebras, C and C prime, such that H3 of C is isomorphic to H3 of C prime as Albert algebras, but C is not isomorphic to C prime. And in fact, worse than that, the quadratic form of C is not isometric to the quadratic form of C prime. So why is this other condition necessary? It's because without it, this was already clear from Philippe Gilles' result, because it is, the implications go in this way. So if you have C isomorphic to C prime, isomorphic, then this implies that their quadratic forms are isometric. And this implies that their Albert algebras are isomorphic. So the dependency of the Albert algebra on the Octonian algebra, if you wish, goes via the quadratic form. So we already know from Philippe Gilles' result that this implication does not hold. So we know that the Albert algebra cannot possibly determine C up to isomorphism, but could it determine at least C up to isometry of its quadratic form? And the answer is still no. Over fields, both these implications hold, and this general chain of implications is called the Albert-Jacobson theorem, that the Albert algebra determines the Octonian algebra. So over rings, the Albert-Jacobson theorem fails to hold in a very strong sense. So this gave some information about the second step of our march onto exceptional groups, which is this one, and noting, connecting to this one. Now, what about groups of type E6? How do they relate to this story? So let me recap with Albert algebras that I told you that one way of constructing Albert algebras is as these Hermitian matrices with the anticommutator as product, and all Albert algebras are twisted forms of such algebras. They become locally isomorphic to these algebras. Now we look more generally at general Albert algebras, not caring about this internal structure. So we look at Albert algebras as just given exceptional Jordan algebras, and we try to understand the torsor 3. So this is the E6 over whatever. What did I actually denote this torsor? I denoted it Sn. So what does this mean? So any Albert algebra has a cubic form. Essentially the determinant in the case of Hermitian matrices. And so it is well known over fields and not difficult to prove over rings that the, let's call this N, the isometry group of N is simply connected of type E6. And so if, in fact, if J is an Albert algebra, and you have some linear map from J to J, then phi is an automorphism if and only if phi is an isometry and fixes the unity of J. So a corollary of this is that the, well, not exactly a corollary, so maybe let me be honest and call it a proposition, if we were to take this seriously. The isometry group of N acts on the somehow unit sphere of this N, so the X in J, such that norm of X equals 1. And this action is transitive up to a reasonable base change. So again, it is FPPF locally transitive. And the corollary part is that the stabilizer of the distinguished element 1J, the unity of the algebra, which has indeed norm 1, this is the automorphism group of J. And so now we can make this torsor precise. So this gives a torsor Eson N down onto Sn, and this is an aut J torsor. So what would this torsor classify? Well, similar to the coming back now somehow to tie things together to the Octonian case, this torsor would classify Albert algebras that have isometric norm forms but are not necessarily isomorphic. Over fields, this is already non-trivial. So over the real numbers, for example, there exist up to isomorphism 3 Albert algebras, 2 of whom have isometric norm forms. But what is non-trivial is that you can take your Albert algebra to be the split Albert algebra. This is the sort of most basic Albert algebra. It is constructed in this Hermitian way from the so-called split Octonian algebra. Put differently, it is the unique Albert algebra up to isomorphism whose automorphism group is the split group of type F4. Over fields, this split Albert algebra doesn't have any non-trivial other algebras with the same norm form. But over rings, it does. So the proposition is that this is non-trivial, even in the split case. And we can also, in the exact same vein as with Octonian algebras, give a similar a similar description of what the twists are. So the twists, or the twist by the fiber of some element P in Sn is the isotope Jp of J. As with Octonian algebras, these isotopes are classical objects. So perhaps the main point of this proposition is that we can now relate this geometric construction to this classical algebraic thing. So let me end by looking forward into the next step, where we look at E7 and E6. Because now somehow we have an understanding of E6, at least those E6 that arise as isometry groups of norm forms. So now we can try to understand E7 in terms of E6. And so to do this, I will just hint at the objects that are there. So if we have J and Albert algebra, we can construct the Brown algebra, B, which is somehow the set of alpha, beta, J, K, with alpha and beta in our ring and J and K in our Albert algebra. So this is an example of what is known as a structurable algebra of type, of dimension 56. Now, the point is that assuming that now 2 and 3 are invertible in the ring, one can extend results from fields to the effect that the automorphism group of B is of type E6 and sits inside some invariance group of some Freudenthal triple system, which is essentially an isometry group of some quartic form. And this group is of type E7. There is also a notion of isotope, and by playing the same game, we can understand groups of type E7 in terms of groups of type E6. To which extent this is possible is a work in progress, and I hope to be able to give you the results at a later occasion. But my hope with this talk is that I have shown you how to, one approach to exceptional groups using other exceptional objects to somehow understand the exceptional groups in their, if you will, right way and their full bloom as symmetry groups of something. And since this workshop is dedicated to symmetry, I felt that this would be fitting here. So with this, I thank you for your attention.